Alright, so today we're going to make a TEM lift out and thin a TEM sample using the Plasma FIB. This particular sample is some kind of a thin film grown on a silicon wafer. And the user wanted us to do this preparation on the Plasma FIB to avoid any gallium implantation. And we're also going to be doing the preparation on a molybdenum TEM grid because copper is an element of interest that they want to look at. So the combination of the moly grid and the Plasma FIB will avoid potential contamination of both of those elements. Now the first step we have to do is to align the Easylift needle. I have already pumped down the system with the sample and the molybdenum grid in the chamber, which you can see down here on the nav cam. And I have put in a new Easylift needle, but we have to calibrate that. Now we could do this later in the process, but it's always a good idea to do it first. That way if there's a problem with the needle, you don't waste a lot of time. You can just vent and change it. So what we'll do is we'll go up here. I already have our electron beam on, and I already have the FIB on. So we'll go ahead and start imaging with the SEM. And let's just move over to the molybdenum grid, and we'll use this to focus and adjust our astigmatism. So we can zoom in on the top of the grid here, we'll focus, get our astigmatism close, and then link our working distance, and we'll set this to 4 millimeters. Now with these TEM grids, when there's no sample on them, you can set the height either by tilting or by just simply imaging with the FIB. So let's do that. We'll just start imaging on the FIB, and we can see the side of the grid here. This is the moly finger, and whatever region we want to attach the sample, we want to be in the center of the FIB. And if we need to, we can move the stage up and down with the slider so that the appropriate part of the grid is right in the center. So this looks pretty good. We'll click add, and we'll call this moly grid. So now what we're going to do is we're going to go to our alignments tab, and we're going to choose Easylift needle exchange calibration, and we're just going to follow the steps here. So first step just tells you what you're doing. We click next. Second step is to vent the chamber and pump it back down. I already did this. I loaded the needle while I loaded the sample, so we're going to skip these two steps and just click next. Now the stage drops 2 millimeters. This is so you don't crash into anything when the needle homes. And now we're going to do the calibration routine. So we just click calibrate, and this homes the axes on the Easylift manipulator. This should run automatically. If for some reason it fails, you can just click the calibrate a second time, and it usually works the second time. All right, so the needle's in. So now we click next. So now what we want to do is to move the needle to the center of the SEM and also to the center of the FIB. So I'm going to change my focus on the SEM, and then I'm going to click and drag the needle with the mouse control to the center of the image. And we don't have to be absolutely perfect, but within a couple hundred nanometers is good. Okay, so that's in the center of the SEM. Now I'm going to go to the FIB. Now for the FIB imaging, I'm going to turn my beam current down a little bit because I don't want to mill away the end of this brand new needle. So we'll drop down to 100 picoamps. And okay, we can see there's the needle. It's a little bit on the low side, so we're going to use the jog Z, and we'll bring it up to the center of the circle. And we're only interested in getting it in the vertical center. We don't care if it's to the right or to the left of center. Just the up and down is important. And this little graphic down here kind of shows you what we're trying to go for. All right, so let's double check on our SEM alignment. You kind of have to do this a couple times with both the SEM and the FIB just to make sure it stays where you think it is. So each time it should get closer and closer. Alright, good enough. Okay, so now we're going to click Next. And now we're going to do the compucentric rotation alignment. So the needle rotates 90 degrees, and the software requires us to bring it back to the center of the screen. Now for some reason you can't use the mouse overlay to move the needle here, so we're going to use these step functions. So we'll just start off with the 50 micron step, and we'll click the needle down. Let's do two down and one right, and then we'll just drop down to the 10 micron step. We'll bring it back closer to center, go to 2 micron, and we'll just keep working our way towards the center of the screen here. Alright. And you can see with the 200 nanometer step, I can't get it perfect, but it's really not that critical. As long as you get it close, it'll work out. So now we say Next. And the software is warning me that the needle is close to the z-axis limit. We're just going to go with it here. Sometimes you have to vent and move the needle, and sometimes you're okay. Let's just click Next, and we'll say Save Alignment, and we'll see what happens here. And click Finish. Now the test, if the needle is going to function for us, is can I move it to the eccentric and can I move it to the park position? So if we go ahead and image with our FIB, and here let's move over to the side just a little bit so we don't crash. If I say insert the Easylift to park, this should come into right about here, 200 microns above the center. And I should be able to say go to eccentric, and it looks good. So we'll be fine to use the needle here, even though that software gave us a little bit of a warning. And we can put the rotation back to 0. All right, we'll go to park, retract. All right, so now I know my Easylift needle's good and calibrated, and I already found the molybdenum grid. So the next step of this process is to trim the moly grid. What you find with these is that the way they make them results in this really, really aggressive curve on the surface. And this can be really, really annoying to try to deal with. If we do our lift out and park our sample right in here in the center, it will be shadowed by these curves. So what we want to do is cut away these things. Now, fortunately, we are on the plasma FIB, which allows us to do very high beam current milling. So it doesn't take too long to get rid of these guys. So what I'm going to do is I'm going to do a small relative rotation of the stage. Let's try maybe 30 degrees. And I'm going to cut off this corner of the grid here, and then I'm going to cut off the other corner of the grid here, make kind of like a little point, and that will be where we're going to put the TEM lift out. So best practices on the plasma FIB is to focus at a 100 picoamp beam current, and then go to the high beam currents and just cut. Don't worry about trying to change your focus or astigmatism. Just trust that the tool alignment is going to be close enough, and it should hopefully work out for you. All right, so we got it in focus. Let's get up to the 2.5 microamp beam because we don't want to be wasting a bunch of time. Let the beam current finish changing, and let's see what we got here. All right, so there's the moly grid. You can see image quality is okay. Not perfect, but it's good enough for what we're gonna do. So we'll go to patterning. We're gonna choose a rectangle pattern. We're just gonna draw a nice little vertical rectangle here. And we can make it, let's make it 100 microns tall, why not? And we'll just kind of position that so that it'll trim off that corner. And let's use the silicon application file, and let's tell it to cut, let's go 100 microns deep. I don't know how long it actually needs. We'll find out here. So let's hit play. And we should see here in pretty short order that that edge is being chopped off with the fib. All right, looks like we cut away about half of it. Let's stop and we'll see what is going on here. Now you get a lot of detector saturation with the big fib currents, so when you're imaging with the SEM, you may have to do some adjustment with the brightness and contrast. So it looks like here we got about half of that cut away. So let's shrink this box down a little bit and we'll do another cut. So as you can see, I put 100 microns for the cut depth, but I'm not really using that for any specific purpose. I'm just kind of eyeballing these cuts. All right, let's see what we got over here. That looks pretty nice. All right, nice and cleaned up. So now what we're gonna do is we'll do a relative 60-degree rotation from this point. That'll bring us around to the other angle. And we want to cut off this side now. All right. Alright, pretty good. We're not quite in the center of the grid, so let's take a little bit more off. It is really nice to do this on the plasma fib. If you have to do this on the gallium fib, this cut takes about an hour to run. So the big beam currents are really helpful on this tool. If you know you got to use a moly grid, you might want to reserve time on the plasma fib first just to prepare the grids, because you can do this in about 5 minutes, as you can see here, and that'll save you a lot of time on the other tool. All right, good enough. We're not perfectly centered in the grid, but not that critical. All right, so let's go back down to our 100 picoamps for our fib. And we'll go ahead and do our stage rotation back to minus 30 degrees, so we're back square. And let's just double check that everything looks nice. So this is now where we're going to attach our TEM liftout. Everything looks pretty good here, so let's go ahead and update our saved position. And now we can go ahead and work on the actual TEM liftout. Now, when we go over to the silicon sample, we're going to try to minimize ion damage as much as possible. So what that means is no fib imaging until we get the surface protected. Now the plasma fibs sometimes leak a little bit of beam current down the column. So if you're really, really nervous about your sample condition, what we can do is simply turn off the fib beam until we're actually ready for it. That way we should have zero ion damage on the surface as we go. All right, so we use our nav cam here. Do a reality check in the CCD camera. So if I move from the grid over here to the silicon sample, I need to make sure I'm not going to slam anything into the bottom of the lens, and everything looks good. So we'll go ahead and just double click on the tip of this silicon piece and move that over to center of the SEM. Now the thin film on this sample is not a uniform coverage, so what we're looking for is this this kind of textured stuff here. This is the actual film grown on this sample. You can see it kind of is in little islands around here, and then this is the actual silicon wafer. So we want to do our lift out in one of these regions inside this kind of stuff here. Just to help the TEM along, what we can do is try to get aligned with one of the primary crystal directions on the wafer. Typically silicon wafers are either cut or cleaved parallel to either 110 or 100 or 111. This one is a cut edge right here, should be parallel to 100. So if I do a horizontal alignment along that edge and then we do the lift out, that should get the sample, at least this direction will be parallel to 100, and oh, excuse me, this should be a 110 direction. So the TEM sample will be parallel to 110, which is pretty typical for silicon wafers. If you do your lift out on a 45-degree angle relative to this, then you'll be parallel to the 100 directions. All right, so I got my alignment pretty good, pretty close, and let's go find one of these spots. We want to look for one of the thicker globs of this stuff here. Like this should be good. All right, so this is the film, and let's just focus on it. We can adjust our astigmatism a little bit. All right, pretty nice. And let's go ahead and take a picture. So let's say our snapshot, we'll edit our snapshot settings. I like 3 microseconds, makes a nice, reasonable snapshot. And we can say File, Save As, and we'll go ahead and save TEM Prep SEM. Save. Okay, so first step in making a sample is we need to find the eccentric height. I can't use the fib to determine sample height because I don't want to damage the surface until I get it protected. So what we'll do is we'll just put a feature right in the center of the screen. We know if we focus on it and link our working distance, we should move to about 4 millimeters, and that'll get us pretty close. So if I look over here, it says we're at 4.00. That's because it was linked to the TEM grid. So we move it to 4, and then we're going to find the eccentric height by tilting. So let's just put the center of this little bare circular region in the center of the SEM, and we're going to do a small tilt. I like 10 degrees. And as the stage tilts, you see that that region moves up. That means our sample is a little bit too tall. So we're going to use our Z stage slider, and we're going to bring the sample down in height so that that region is back in the center of the SEM. And then we can tilt back to 0. And now that we're at the eccentric height, we should be able to go back and forth through the tilt range without this thing moving too much. And it also means we're safe to insert the gas injector. All right, so now let's find our region that we're going to do our lift out. We're going to use the deposition system called the Multichem. So I'm going to go to the patterning tab, and we have a Multichem on this tool. It has platinum and carbon, and I'm just going to say insert Multichem, and that'll go ahead and insert. Now, normally this goes in very fast. It's taking a few more seconds today because I shut down the tool, so it had to initialize the Multichem. But there's the Multichem needle. It is movable. It can move around to different positions if you need it to. I don't think we're going to use any of that today. So next up, let's go ahead and draw a rectangle pattern on the screen. This is going to be where we do our deposition, and we will choose an application file. Let's just go ahead and do, let's do just platinum for now. And we're going to do a 20 micron wide bar. We'll do 2 microns for the Y dimension, and a couple hundred nanometers is really all you need. And let's try to see if we can squeeze this in between some of these bare spots in here, like maybe right there is good. Now the beam current we need is going to be a little bit higher than 0.2 nanoamps. So generally for SEM depositions, you want low voltage and high beam current. So let's drop our voltage down to 2 kV. And I'm going to increase the beam current up to, let's try maybe 6.4 nanoamps. We'll double check our source tilt. Let's just move that down a little bit. And if we're concerned about any kind of image quality, we also want to check our astigmatism and our lens alignment. Lens alignment's off just a little bit here. You can see a little bit of wobbling, so let's go ahead and move that. Now you can see at this high beam current, the surface is getting a little bit contaminated. For SEM imaging, that's bad, but we're going to coat this thing anyway with platinum, so coatings are good. They'll protect the surface. Just be a little bit of carbon instead of platinum. All right, so everything here looks good. I don't think I need a micron for Z. Let's just do half a micron. And it says that'll take a minute. And let's save file, save as, save our overlay graphic on this one. All right, everything looks good, and we'll go ahead and hit play. All right, so the goal of this is not to build up the full protection layer. The goal is to put enough platinum down so that the FIB does not destroy the top of this thin film when we do the FIB deposition. So you really only need about 100 nanometers or so of deposition. Generally, if you're not sure, or if your calibrations are suspect for the deposition rate, just deposit until you can see a bump sticking off the surface, because if you can see the bump in the SEM, you probably have enough material to protect it from FIB damage. All right, so that's done. Let's go ahead and change our beam current back down to something a little more reasonable. And we can, let's just hide this pattern for now, just in case we need it again. All right, that should be good. So I'm going to take out the Multichem. And now we will go ahead and tilt the sample to 52 degrees. And then we will add more deposition onto this region of the sample using the FIB. We're a little bit off on the eccentric height. Let's just go ahead and fix that. It was pretty close, but let's make it perfect. And since we're looking at a tilted surface, let's turn on our dynamic focus. That way we'll keep the whole surface in focus. So you can see a little bump of platinum here. It should be enough to keep the xenon ions from getting into the surface until our deposition starts growing. So we should be good there. So let's go ahead and put the multi-chem back in. Had to retract it in order to tilt the stage. All right, multi-chem's back in. Let's take a picture here just so we can monitor, track our progress. Let's say file, save as. This time let's go back to 16-bit. Now for the fib, I gotta turn my fib back on, so I say beam on. And we're going to use a fairly small beam current here because I want to avoid sputtering away this platinum until we're ready. Now, I might have to do another lift out next to this site, so I want to confine all of my ion damage to a small region if possible. Good way to figure this out is if I look at with my SEM image, I'm at 8000x magnification, or you can look at horizontal field widths if you want to think in that dimension. And if I go to my fib's currently at 650x. So if I start imaging with my fib, I'm going to damage a real big area of this sample. So before I hit the pause button, I'm going to turn up my magnification so that it's also 8000x. That way the fib should only expose a fairly small area of this sample where we're going to do the lift out anyway. Now you can force the issue over here in the magnification selections. There's a couple magnifications. I personally hate this. I like being able to do separate adjustments on the two SEM and fib beams, but some people like this. If you turn that on, it just forces them to always stay the same. The next thing we're going to do is we're only going to use snapshots with the fib until we figure out what we're looking at. So I can right click and say edit my snapshot, and I'm going to change my dwell time to 100 nanoseconds, which is a nice fast scan, and we're going to say go, snapshot. All right, so I get an image here, and I can see I'm looking at, this is the side of the platinum deposition that I did. So the center of the bar is over here to the right, so I need to beam shift the fib to the left. So I hold the shift key down, click on the right edge of the image, and I'm just going to drag that region to the center, let go, and we'll take another snapshot. And I didn't quite get it all the way. Let's try that again. All right, pretty good. So now my fib is beam shifted to align with my SEM image. I can adjust my focus and astigmatism. Again, we want to do this at 100 picoamps. That's kind of the anchor current for the plasma fib. And we'll take one more snapshot. And at this point, I can go ahead and image as much as I want, either down here or up here, because the area underneath the platinum cap is the final sample. So as long as I don't sputter away that, I should be good to go. So we go ahead and start imaging here, and I'm going to adjust my focus, adjust my astigmatism as best as I can. Pretty good. Let's turn up the resolution on that. And let's do one more snapshot just because. Oop, there we go. All right, so now we're going to go ahead and draw our pattern. And our deposition, we have platinum, we have carbon. If you deposit platinum with the xenon beam, it makes a very, very, very soft deposition, and you cut through it very easily. If you deposit carbon, it makes a very, very hard deposition, which can also cause trouble trying to cut through it. One of the neat things with the multi-chem is that we can actually blend gases. So if you do a little bit of carbon and a little bit of platinum, you can tune the hardness of the deposition to get what you want. So we have an application file on here just called carbon plus platinum. We made it during the apps training we had, but go ahead and use this. And if we look in the advanced properties of this, you can see that it does both carbon and platinum at the same time. It's doing 100% platinum gas flow and 2% carbon. And this is a pretty good blend for working on materials like silicon or equivalent hard materials, some of the semiconductors, things like that. So let's go ahead and set our pattern dimensions. We'll do 20 microns for X, 2 microns for Y, and let's do 3 microns for Z. Now our beam current's a little bit low. Generally you want about 6 to 10 picoamps of beam current for every square micron of area. So this is 20 times 2, it's 40 square microns of area. So we want about 400 picoamps or so of beam current. So if we go up here to our beam current list, we're on 100 right now. We have a 300 and we have a 1,000. If we want to make sure we don't accidentally wreck the sample from a mistake, maybe we should go with the smaller beam current. So let's go with the 300 picoamp aperture, and that should be good enough. So we'll go ahead and do one more snapshot just to make sure everything looks good. The fib hadn't finished changing the beam current yet. There it is. Focus looks a little bit off here, so let's check our focus and astigmatism. You can see we're sputtering away the surface much faster with the higher beam current here. All right, pretty good. We'll put our pattern right on top of the previous spot, and let's go ahead and save that image. TEM prep. This is going to be fib number 1. Save. And this is going to take 13 minutes for the 3 microns of deposition. So we're going to let that run, and we'll see you back here. So whenever time you get this warning, it means you got 2 patterns. So if I hit cancel, if I go over to my SEM, I have a pattern in the SEM too. So the software is just trying to make sure you're running the right pattern. I always think it's a good idea to only have one pattern up at a time so you don't make mistakes. So we'll go ahead and hit play. And this should be running now. There it goes. So we're injecting both gases, and we should be hopefully getting a nice deposition already. If we want to check, we can do a snapshot with the SEM, and we can see we're already starting to grow a film on top of the previous platinum deposition. You can see down here where I did my fib focusing, where it's already sputtered away the surface a little bit. So, yep. So anyway, we'll see you back in about 13 minutes or so. Okay, we're back. It's been about 13 minutes here, and our pattern is almost done. And I took a snapshot while it was running just to kind of check on its progress here. And let's do one more final image here. And you can see we've got this really nice thick capping layer on top of the region of interest now. Now if you remember over here in the settings for my deposition, I said I was only going to do 3 microns thick. And this is the result. And if we measure this, make sure our tilt correction is turned on, it's actually more like little over 7 microns thick. The reason for that is when we made this application file, we did not calibrate the deposition rate. You can do that. It involves basically doing a test deposition and then back calculating these parameters in the application file so you get the right thickness. We just haven't really bothered with it yet. But you can, rule of thumb is with this particular application file is it'll deposit about twice what you tell it. So if you need a more precise deposition thickness, you can go by that method. So let's take out the multichem. We're done with that. And now what we're going to do is go ahead and cut away the material on either side of this to prepare for the lift out. So I'll say file, save. Now, for this, I'm going to use a much higher beam current because I don't want this to take forever. So let's go with the 60 nanoamp. Why not? Take a snapshot for sure. And we can see our region here. Let's just double check that our beam is fairly well shaped. So we're going to do a spot mode. And that's not too bad, actually. So the shortcut keys for that are Control K to go into spot mode. Put the spot somewhere where you don't care about, and then Control B turns off the beam blanker, let it sit for a few seconds, and then Control M goes back to imaging mode, and then you take a snapshot. So I can see this is how big my beam is at 60 nanoamps. And let's go ahead and place a regular cross-section pattern on the bottom side of this sample. I always like to make it a couple microns wider in both directions, so let's go 30 microns for X, let's go 20 microns for Y, and let's go 20 microns for Z. And let's see what that does. We'll make sure this is nice and deep. The center of the beam will go right along this yellow line, so if I put this right up next to my deposition, I'll probably wreck everything that I did. So I want to make sure I know how big my beam diameter is, and I'll just scoot this down a little bit so that I'm not right up next to the platinum. So something like that should be good. And then I'm going to do Control C, Control V to copy that pattern. I'll put another one up here on the top, and I need to change the scan direction to be top to bottom for this one. Just kind of make them symmetrical, something like this. File, save, and both of these will take 2 minutes and 40 seconds each, so we'll go ahead and hit start. And this total time is 5 minutes and a few seconds here. I should mention the application file I'm using is the Silicon Multipass. This is probably the best one to use for the regular cross sections if you are working with anything that's similar to silicon in terms of its hardness. So that's about one pass through. It should do 4 passes. Let's take a look and see what we're doing. Pretty nice. You can see the holes that I cut here with the 60 nanoamp beam. All right, 2 passes down. Let's see what we're doing. Again, these high beam currents saturate the detector. It takes a few seconds to get your image quality back on the SEM. Control R is a really good shortcut key to remember because it restarts the SEM scanning. So you can keep hitting Control R until the image looks good and then let it run through its scan to take a picture. What I'm looking for with these cuts is I want to see the bottom of my trench disappear behind this edge. So that was 2 passes with the regular cross section, and we're just about there. So the 3rd pass will definitely cut this as deep as I need. and the pattern is going to run 3 passes total. So this is just about perfect for what I want to do. So once that pattern is finished, it'll then hop up here and it'll do the second pattern, scanning from the top down. So let's see what our result looks like. All right, just get my brightness and contrast okay for this image, and that looks really nice. File, save. Should get the same result on the top cut as we got on the bottom cut, except that it's mirrored, so the deep end will be close to the sample instead of on the top here. While we're waiting here, one thing that's always really good practice is once you start working on a site is to save your stage position. That way, if you do something stupid like move the stage, you don't have to spend a whole bunch of time hunting around for your lift out site again. You can just go back to the saved position. On this type of sample, this would be pretty easy to find this lift out again, but on some samples, the surfaces are really rough. And it can be a real nightmare looking for a lift out site if you lose it. So we got about 30 seconds left with this pattern. When this is finished, I'm going to drop my beam current on the fib to the next lower value, which I believe is 15 nanoamps, and then we're going to do cleaning cross sections to remove some of this material that's still adjacent to the region of interest. Alright, so let's delete our patterns, drop the fib to 15 nanoamps. While we're waiting for that to stabilize, let's go ahead and take our picture of our progress. Looks pretty nice. Go back over here to the fib, we'll take our snapshot. Now again, on the plasma fib, focusing can be rather tricky, so as long as the image looks pretty decent, I wouldn't worry about it. More than likely with the big beam currents, you're just going to get it more out of focus than where you start with. Let's see what our spot looks like. So we'll put spot up here and say turn the beam blank off, and let's see. Now this one looks like it's a little bit out of focus. We got a pretty big halo around the center spot, so I am going to try to focus this one a little bit. So let's see how we can do here. Got a little bit of astigmatism too. So adjust my focus, adjust my stigmators. All right, Control K, Control B, Control M. Let's see if we got any better. Oh, focus is better. Didn't fix the astigmatism though. I made that worse actually. All right, that's better. Maybe not perfect, but it's good enough for now. So we're going to do a cleaning cross section. We'll draw that across the bottom here. We'll do our same dimensions, 30 microns for the X. The Y I'm going to set based on what this looks like. Let's zoom in here a little bit. So we want to get rid of all this edge, plus a little bit extra bonus space there. And then for Z, we'll do 20 microns. The silicon CCS file is self-consistent with the silicon multipass, so we should get the same depth of cut as we got with the regular cross-section. So that should look pretty good. It takes about 2 minutes and 40 seconds. This looks good. Let's save our picture and we'll say go. Later on, when this Liftout is attached to the molybdenum grid, we'll use these cleaning cross sections to thin the sample down to electron transparency as well. So we take a snapshot, we can see here we're cutting away this edge from the bottom up. Okay, let's take a snapshot with the SEM. Let's see what is going on here. So much cleaner edge right here. We still haven't gotten all the way into the protected region of interest yet. Because when that happens, we should see the discrete layers of the platinum deposition, or the platinum carbon deposition, the platinum SEM deposition, the layer on the surface of the wafer, and then the silicon substrate. So we should see all those layers discretely. Alright, so not quite there yet. So what we're going to do is we're going to do a little bit more cutting, slide the top of this pattern up slightly, and we'll just run that again, because I really want to make sure I have this edge all cleaned up before I do my lift out. That looks pretty good, so I'm going to go ahead and stop my cleaning cross section. And now we'll do the other cut. So we'll change our scan direction to be top to bottom and set it up kind of like this and say go. Even though we can't see what's going on with the SEM, it's still a good idea to take a snapshot every so often. Just make sure you're not doing something dumb, like cutting through the center of your sample. Alright, so should be all set here. So now we're ready to do the undercut, and then we'll do the lift out. So after I take a picture here, we will go ahead and tilt the stage to 0 degrees. So since the fib is at a offset angle to the SEM, this will now allow the fib to cut through the sides of the lift out chunk and cut underneath it. Okay, and we'll delete our cleaning cross section and we'll take a quick image here. All right, we'll use our beam shift. Alright, so there's the side of the sample, here's the platinum deposition, here's the sample. This will appear to be upside down in this orientation. So what I want to do is I want a set of 3 rectangle patterns to cut the left side, bottom, and right side. I'm going to use the silicon application file for this. We'll do one like this, one across the bottom, and one on the right hand side. And the one on the right hand side, I want to leave a little bit of the silicon behind so that this doesn't fall off into the pit. Something like that should do. And I want to run all 3 patterns in parallel. And let's say select all, and let's just do 5 microns for Z. And that should work good. So let's hit go. So this starts running. And this shouldn't take too long with this beam current. I'm still up here at the 15 nanoamps. Now, you don't want to place your horizontal cut right at the bottom of the pit. Generally, it won't cut through the sample. You always want to have it about halfway to 2/3 of the way from the edge of the sample to the edge of the pit where you can see. So in the real-time view here, you can see these kind of dark areas forming here and here. Those are holes in the corners. The way I draw these patterns, the patterns overlap on the corners, so it'll usually cut through these two areas first because it's double cutting there. And then the sidewalls will go second, and then last you should see the bottom get milled away. So we know we're done when this edge right here and this edge right here come together and meet up in the center. The image is a little bit pixelated, but you do this a couple times, you get an idea of what you're looking for. It's much easier to see this on a gallium fib just because the resolution of the cut is better, so you can see a lot more detail in here as you're cutting this. So if you're not really sure what you're looking for, maybe try to do a lift out on a gallium fib once, and you'll get an idea of what that looks like. So we're just about there. Again, I want to see this kind of gray thing go away. Alright, so now it's starting to shrink. It looks like it's not connected anymore. There might be a little bit of a connection right there. So let this run for another couple seconds. Alright, I think that's good. So let's go ahead and hit stop, and we'll double check with our SEM image and see. And in the SEM image, we should see this kind of upside down shape, J shape, cut into the sidewall of the lift out trench if everything went according to plan. And it does look like we achieved that. We can see the cut going all the way across the bottom, so we should be good to go there. Now I like to remove this redeposited material. As the fib hits this back surface, it tends to launch sputtered ions onto this face, and it builds up this kind of crummy layer. I like to get rid of that. The easiest way is to simply go back to 52-degree tilt, drop your beam current just a little bit, and do a rectangle cut, and that will go away rather fast. Alright, so take an image, beam shift down, beam shift. Alright, so there's the side of the sample. I'm going to go pattern tab, do a rectangle just like that. And we'll say go. And within just a few seconds, that material should be sputtered off of the face. Not even worried about depth of cut. It's set to 1 micron over here, but it's not really even important. So there you go, nice and clean again. So you got the platinum, the silicon, the layer of interest is in the middle there. We can see, let me slow the scan down a little bit. You can see the gap all the way around the sample, except for right here, so we know that we're good to go with the lift out. So now we're going to drop our beam current on our fib down to 30 picoamps. It's good beam current to use for doing the lift out. We're going to set our tilt of the stage back to 0. And we're going to make sure that our beam shifts are zeroed out on the SEM and on the fib as much as possible. And the reason we're doing this is we calibrated the Easylift needle based on no beam shifts on the SEM or fib. So what I want to do is have this lift out right in the middle of the SEM without any beam shift, so I can right click and say 0. And then I also want to go to my fib and say 0 the beam shift. And I want to make sure that that lift out is right in the center of the fib. And you can see that it's actually a little bit high. So I'm going to use my stage Z control here and nudge this down slightly. So that way the sample, as much as possible, is lined up with the Easylift alignment. And we still have to do a left-right adjustment here, but that's not a big deal. Alright, so now we should be ready to go. Let's update our lift out site. So I'm going to go to Easylift, and I'm going to say insert to park, and that should bring the needle in. And because I just aligned it, this needle should be 200 microns above that surface. Now if I look with the fib, I can't see the needle yet because it's outside my field of view. But if I trust my alignment of my Easylift really closely, what I can do is go over here to step mode, and I'm going to move it up 2 clicks with the 10 micron step. So I'm going to click 1, click 2. So now I should be 220 microns above the surface. And then I'm going to click 100 microns and click once down and twice down. And let's go back to jog mode so I don't make a mistake. And so now the needle should be 20 microns above the surface, and it's right there. Next up, let's bring in the multichem. We're going to need that to weld the end of the needle to the side of the sample. So here comes the multichem. And we'll go ahead and move the Easylift over to the side of the sample, and we will attach it to the side. So I'm going to use the mouse overlay to drag the Easylift around. I like this interface. It's really smooth, really nice. Easy going here. Now we don't actually have to touch the sample if you don't want to. Just get close like that, and then we'll go ahead and draw a small pattern right here. And this time I'm going to use carbon depth. The only reason for that is it's hard. It'll hold onto the sample really well, and it deposits pretty quick. So we don't want to be waiting around for this to deposit. So you can see here in the real-time image, the carbon is growing on all these surfaces. They'll start to get kind of fat and blobby. And once you think that the needle is sufficiently attached to the side of the lift out, then we'll go ahead and stop the deposition. Shouldn't take more than about 30-40 seconds if you've got your parameters correct. Alright, that should be good. So I'm going to hit stop. And then I'm going to beam shift over here so I can see the connecting tab. And we'll turn up our beam current, and we will cut through that. So I'm just going to use a little skinny rectangle pattern. We'll set that to silicon. Maybe do a couple micron depth. Do a snapshot. I'm not too worried about focus. It looks okay. So something like this. And we'll say go. And that should cut through that within a couple seconds. Alright, done. Double check with the SEM. We can see that that whole bridge has been cut. And if I'm really not sure if I'm totally free, what you can do is tap on the side of the microscope table, gently at first, but if I go tap on the system, you can see that the sample and the Easylift vibrate together, and that tells me that it is safe to do the extraction. So let's turn my fib back down to 30 picoamps so I don't wreck my sample. We'll start scanning, and then we'll go jog Z straight up. Okay, out of the pit, I'm going to say retract. And then we'll also retract the multichem. And now we're going to head back over to the molybdenum grid, which I have the sample position saved. So I'm just going to click Molly grid. We'll head over there, and then we're going to deposit the sample onto this corner that I prepared using a carbon deposition. So make sure everything looks good. Yep, remember the fib image is upside down. So we're going to say insert to park. That'll bring the sample right about here. And we'll go ahead and move it over to the side. Bring it down. Let's bring in the multi-chem. All right, and let's make sure we're lined up right on that little point that I made. All right, and we'll go ahead and drag it to the right. And this time we actually want to make contact with the grid, but just barely. Right there. Okay, so let's go ahead and attach that with a weld. Let's turn up our beam current. About 100 picoamps is pretty good for this. We'll do carbon, and just a half a micron is good. And we just want to get this little gap in there. Actually, I think we need a little bit more beam current. Let's go up to 0.3 nanoamps. Looks good. And the idea here is we don't need to completely bury this thing in carbon. We just want to get the sample attached to the moly grid. And then what we'll do is we'll add more depositions into these corners. And we'll rotate the stage a little bit. It'll make it go a little faster. So all I'm looking for here is I want to see some of this crack, this gap between the moly grid and the sample, just kind of fill in with carbon. And that should tell me that I've got it stuck to the grid. So this should be good. And we'll beam shift over to the side, and then I'm going to cut that little guy free. Now since that thing is so tiny, I'm just going to stay at this beam current, the 0.3 nanoamps, and it should cut through that with no problem. All right, I think that's done. Nope, not yet. Let me just make that full screen just to see it a little better. There it goes. Okay. So we want to back off the Easylift, send it back to its retracted position, and what I'm going to do is take out the multichem, and I want to rotate this sample so that it is facing the multichem direction. This will get us more deposition rate than when the sample's flat. So let's go ahead and put the multichem back in. Alright, so now let's put a pattern on there. We'll say we're going to do carbon again, and let's just do like maybe 0.3 microns. And we'll say go. And then once this is done, I'm going to rotate the stage again, another 90 degrees clockwise, and then do another one of these carbon depths on the back side, so right on this side here. So this will be welded, the gap is welded with carbon, and then there'll be a layer of carbon deposited on each side, and that should help hold this thing to the moly grid. You don't always need to do this much deposition, but it's really a shame if you drop your sample and the lift out falls off the grid, and that unfortunately tends to happen more frequently with the moly grids. I don't know exactly why, but the samples don't always stick to them quite as well as the copper grids. So a little bit more deposition is a good idea. Alright, so if we take a look with the SEM, you can see here we got this carbon patch right there. That's what we're looking for. Take out the multichem, do a relative 90-degree. Positive rotations are clockwise, so this will be a clockwise rotation. There's the lift out. Put the multichem back in. Rotate. And then we'll fill in this backside. Alright, looks pretty good. So let's delete our pattern. Let's go back to our original rotation angle. So we're doing minus 135 rotation. And actual, and we'll tilt up to 52 degrees. So let me get the sample in position. I want to make sure it's centered under the fib this time without any beam shift. And then if I look with my SEM, I want it to also be centered under the SEM. And I'll change the height of the stage to accomplish that. Alright, looks pretty good. Now, I'm going to use 5 kV for my imaging beam current initially, and I will explain why I'm doing this as we get a little further into the process. But basically, I'm using the accelerating voltage of the SEM as a way to track the sample thickness. source tilt is a little bit off there. And I'm not looking for really perfect imaging in this, just don't want it to be distractingly out of focus though. Okay, so here's our starting point. So we got our SEM lined up, we got our FIB lined up. All right. Now anytime we cut with the FIB, we always have to increase our tilt angle a little bit. So 52 degrees makes this sample parallel to the FIB column. I'm going to add 2 degrees to the tilt, so we're going to go to 54 degrees. And at this tilt angle, we will be cutting on the bottom side of this face here. As you can see, it got a little bit more prominently exposed to the beam. And if we want to cut on the other side, we're going to go to 50 degree tilt, so +2 -2 degrees. Let's turn up our beam current a little bit so we're not sitting here forever. We can probably go with the 15 nanoamps initially. And let's try our best to make sure that we're in focus and that our astigmatism is adjusted. And we're going to do a cleaning cross-section pattern, and we'll do that same 20 micron depth of cut. So that looks pretty nice. And we'll say go. So about 45 seconds or so for this cut. Not too bad. Now as this is going, we want to be careful, because if we screw up our sample at this point, we got to start all over. So we want to take snapshots with the FIB and snapshots with the SEM and make sure we're not cutting too aggressively into the sample. I'm going to stop because I think we're getting a little bit thin there. Alright, so now what we want to do is let's tilt to the 50 degree condition. And now we're going to cut from the top side down. So we change our scan direction on our pattern. That. Alright, so now we did our kind of our rough cuts. So what we're going to do now is drop our beam current down, and we're going to do our cleanup cuts, and that will bring this down to the final thickness that we're going to aim for at 30 kV. So we need to change our scan direction again to be bottom to top. Let's make sure our FIB is in focus still. Alright, now on a sample like this, one strategy that we can employ is, instead of trying to thin the whole thing from the top of the platinum down to the bottom of the silicon, I'm going to try to thin it down to about halfway into this silicon substrate. Keep the bottom kind of thick, and it'll act like a good support. So what I'm going to do is I'm going to take my Z value and I'm going to drop this down to something like 5. Let's center this up a little bit better so I can zoom in on it. Alright, so we're going to put this pattern kind of right up to the edge. Something like this. And I know that this is not going to cut away the entire side of that sample, but that's okay. That's what we want to do. I'm going to say go. And let's start watching this now a little more carefully. Let's turn on the I Spy, and let's look every cleaning cross section, and we'll see what happens here. Alright, now that didn't really do anything, so what we're going to do is we're going to scoot the pattern up just a little bit closer to the top edge, and we're going to run that again. I'll probably slide this bottom edge up too. And as this starts to get thin in the silicon, it'll start to get brighter. And what I'm looking for is a nice even brightness in the silicon right below the region of interest, and that's going to tell me that we're about 200 nanometers thick. And I know that from experience that if you're at 5 kV SEM imaging and the silicon turns bright, you're about 200 nanometers. And that's where we're going to switch to our low voltage and start doing our low voltage milling. And as this gets thinner, the platinum is going to also shrink because we're creating kind of a taper here. So that will naturally get shorter and shorter as we go. Alright, that looks pretty nice. Sometimes you can see this step in the sidewall here, but we must have a fairly gradual taper. So it's not showing up. So now we're going to go to 50 degrees. And we're going to do that same exact thing from the other side. So we're going to top to bottom. Position the pattern right about there. Hit play. And then, of course, we want to be watching with the SEM. You can see here on this side, this is getting bright. This is what I want to see, this kind of contrast across the whole area. There we go. There's a little bit brighter right here. So maybe 1 or 2 more cleaning cross sections and we'll be hitting the stop button. Yep, let's stop. So now you can see I've got a pretty good idea of where the thin spots are. It's relatively thin up here, but then it gets thick, and that's where the contrast changes. So very thin over here, pretty uniform across this way. I could probably cut this one more time and we'd be okay. So let's we'll go ahead and do that. We're just going to run this pattern one more time just to get that a little bit more even. There we go. Okay, so we got a nice Nice bright, evenly bright area going all the way across here. We lost a little bit of the left side, but that's okay. This is a 20 micron thick sample. It's pretty big. And the bottom is thicker than the top, so that'll help keep this thing from curling up as we do the final thinning. So now what we're going to do is drop our fib to 5 kV. And let's get rid of this pattern. Let's go to, let's try the 0.3 nanoamps. That should be good. Now if I want to see my contrast change again as this gets more and more thin, I got to lower my SEM voltage. So instead of 5 kV, let's drop down to 3 kV. And you can see at 3 kV that the silicon has now turned dark and is no longer electron transparent. So now as it gets thinner and thinner, it will turn bright again, and that'll tell me when I've reached a new target thickness. Now at 3 kV, we have to increase our tilt angles a little bit, so instead of plus and minus 2 degrees, let's do plus and minus 4 degrees. So we'll go to 48 degrees. And let's see what our fib image looks like here at 5 kV. Not too bad. We're going to do focus and astigmatism. Remember that on the Helios instruments, there is a alignment you can do at low voltage. So we can do the L2 modulator. And this is sort of like doing lens alignment. And you want to get rid of that image wobble by adjusting the quadrupole alignment. Especially at the real low voltages, this helps a lot with your image quality on the fib. Yeah, that's pretty good. There's also stigmator sine and cosine adjustments, but I'm not going to worry about that. They're not super critical for this. Astigmatism adjusters aren't very sensitive at low voltage on the fib, so sometimes it's better to go grab the mouse 2D adjuster here and use that for your adjustment. Sometimes it's a little bit faster. And we're not going for any kind of very precise patterning at this point, so if we're a little bit out of focus, it's not a big deal. You definitely get more control with your cut if it's in focus, but this is just sort of a gentle polishing step anyway, so it's not really that critical. So we're going to put just a rectangle pattern on there this time. We're going to do top to bottom with our scanning, and since it's a rectangle pattern, our iSpy is going to be set up based on time. So let's look every maybe like 5 seconds. That should be okay. And what we're going for is we just want to sputter until some of this platinum is removed, or until we start to see the silicon become bright again at the 3 kV beam. All right, play. And my pattern is a little bit wider than it needs to be, so let's shrink that down. And now we just sort of watch it. Now it looks like we're getting a little bit thin over here on the edge, so what I can do to help prevent that is, instead of running my pattern across the whole sample, I can kind of bring it in a little bit so I'm not milling out on this left edge. And what that'll do is it'll probably create a little bit of a step in the thickness profile, but it'll keep this edge from shrinking its way over to the right. So So we're starting to get some electron transparency again here in the silicon at 3 kV. So that's good. It tells me this is getting nice and thin. Alright, let's go ahead and stop this. I want to make sure I mill it from both sides, so I don't want to go too far on the first side. Got to leave a little bit for the second cut. So now we'll go 52 degrees plus 4, so that's going to be 56. Obviously watch out for your TEM grid holder here. You don't want to crash into the side of the lens, which can happen if you get your tilt angles too high. Alright, so this time bottom to top. Let's make sure our images still look good here. Play. And we'll start watching this. Alright, just like before, I'm going to shrink this pattern in a little bit so that I'm not cutting on the end. Alright, I think that looks pretty nice. So then as a final step, we're going to drop our fib down to 2 kV. And we'll also drop our SEM to 2 kV. And we'll do one more polish to make this nice and clean and thin. We're going to do another degree with the tilt, so we'll go 57. You can see here, even at 2 kV, I've got some regions of the silicon that are electron transparent. So, oh my. Okay, so 2 kV imaging starts to get a little bit rough on this tool. But we can still at least see where we know our sample's right here on the end of this point. And if we do the L2 modulator, this will help a little bit. L2 is just the second lens. It's the more or less it's the objective lens for the fib column. And then check our astigmatism. So put our 2 kV pattern on here and let's hit play. And we'll let this cut for another minute or two on each side until it looks good. Let's just double check our pattern placement here. I think I want to scoot this up just a little bit. So the thin area is showing up down here below the surface, which tells me that my over-tilt angles might be a little bit aggressive. So I'm going to bring this back down. Let's come back down to 56 degrees and see if I can get this to thin a little bit nicer. Oh, another thing that we can play with is the pixel pitch of the pattern. So right now the pitch is running a fairly coarse. It's a 390 nanometers. Let's bring that down. Let's try maybe like 50 nanometer pitch. And you see it changes that for both X and Y. That might help smooth out the cut just a little bit here. So now it's scanning a much finer pitch in that rectangle pattern. Should always be seeing something happen as you take your I-Spy images. So like if I put my mouse on the top edge here, the platinum, you can see that it is slowly shrinking with every image, which tells me that I'm actually doing something. Alright, let's cut on the other side for a little bit, and then I think we're going to say this is done. So let's go back to the 48 degrees. Change our pattern to be scanned from the top to bottom. think I'm going to change this up a little bit again. Let's go to 49 degrees. Just because I'm trying to get this a little bit more evenly cut. That looks pretty good. Let's go do one more cleanup on the other side. So 55 degrees, since we're doing plus and minus 3 degrees now. And when you're doing this, you always have to adapt your recipes depending on what you see. So I thought I knew the tilt angles to use, and it wasn't producing the result I wanted, so it changed it up a little bit. Alright, I think let's call this done. We're starting to get a little bit of brightness here in the deposition layer. At 2 kV, that means that this is pretty thin. Now of course you could always go thinner than this, just keep cutting away at it at 2 kV, but I think this will be perfectly suitable for what the user wants. He wants to do EDS, so a little bit thicker is actually better. You get a little bit more count rates there. So that should be good. Let me go back to 52 degrees, and we'll take one final image here just to kind of document the final condition of this thing. That looks pretty good. Let's slow our scan speed down, get a nice pretty image. right, all finished. Let's see, we started at 12:42 and it is now 2:26, so we're looking at about about an hour and a half start to finish for full lift out and thinning. So all right, let's hit the vent button and we're all done. Vent. All right, thanks for watching.